So let's look at a second example of a power series and see if we can figure out its radius of convergence. Okay, so remember, we always have these three options. Either it converges just when x is equal to c, or maybe it's for some little window around c, or maybe it's for everything in the universe. So here's our power series here. This one looks a lot more complicated. We've got this crazy exponent, we've got a factorial going on. One of the things I want you guys to start seeing as a pattern is when you have factorials, the test for convergence that's most likely to work is the ratio test. Okay, so we learned a lot of tools in Unit 3. We could go down our list and try to arrive there, but in general, if I see factorials, I'm thinking probably the ratio test is going to be the way to go. Okay, so let's try out the ratio test here. Remember, for the ratio test, we're supposed to find the limit as n approaches infinity of the n plus first term over the nth term. So let's try that out. Okay, so we're going to do the limit as n approaches infinity of the absolute value of, now looks like an is just that expression in there, right? That's the nth term of that series. Okay, so let's find the n plus first term by plugging in n plus 1 instead of n. Okay, so we have some cleaning up to do, but that's the n plus first term. Now, let's just plug in the nth term for the bottom of my fraction. Okay, so if this is going to work, then we need to make sure that that whole thing is less than 1. That's what we're going to be trying to solve. Alright, so before I do anything with the limit or with that inequality, let's just see what I can clean up here. So the first thing I want to notice, I've got absolute values of a -1 raised to something. Those terms are just going to go away. Okay, whether it turns out to be a -1 or a +1, absolute value, it's just going to be 1. So let's see, I've got x to the 2n plus 3 over 2n plus 3 factorial. And then I've got x to the 2n plus 1 over 2n plus 1 factorial. And still, I'm interested in the end to see when that limit is less than 1. Alright, well I've got a fraction over a fraction, so we're going to do that standard trick for the ratio test, where we take the guy on the top, and instead of dividing by a fraction, we're going to multiply by the reciprocal. Okay, so we should get some nice cancellation here. We've seen this trick used before where we have one factorial over another factorial. A lot of stuff should cancel out. And I should just be left with, let's see, 2n plus 2 and 2n plus 3 on the bottom. Those are the only terms that won't cancel out from those factorials. Now for these exponents, x to the 2n plus 3, x to the 2n minus 1, if I subtract those exponents, I would just get x squared. Okay, so once again, I'm trying to see when that limit is going to be less than 1. Okay, so imagine picking any x value, like maybe I pick 5, or 0.3, or 172. If I let n approach infinity, then essentially I've got some quadratic thing with n, and I've just got a number divided by that. Okay, anytime I do some number divided by a quadratic term, then it's just going to turn into 0. Okay, so that whole limit just turns into 0. So if I was asking myself which values of x cause that limit to be less than 1, it doesn't even matter what x is. All the values work. Okay, so really, there's not just a window around x equals 0 for this guy. Right, notice this is x minus 0 raised to a power. So it's not just some window around it, and it's not just the number 0, it's actually every single value of x we could pick, no matter what. So the radius of convergence here is just going to be equal to infinity, which just tells us plug in any number you want for x, this guy is still going to converge.